Hi, good afternoon, everyone. Today, I will present a topic about iOS and macOS kernel security. The title is Internal Wall in XNU Kernel Objects. I will not only discuss the attack techniques, but also the defense mechanism as well. So let's start our talk. Firstly, let me briefly introduce myself and my teammates. My name is Min Zheng. You can call me Spark. I'm a security expert at Alibaba. I got my PhD in the COHK, and I'm a member of Blue Lotus and Insight Labs. I presented my researches at ISA, Black Hat, DEF CON, HITB, ISC, etc. My teammate is Xiaolong. He also works for Alibaba. He is a PhD from Tsinghua University, and he published papers on Big Four. Okay, let's start our talk. We know that jailbreaking in general means breaking the device out of its jail. And Apple devices are most famous jailed devices among the world. iOS, macOS, watchOS, and tvOS are operating systems developed by Apple and used in Apple devices. All Apple systems, they deploy a same hybrid kernel structure called XNU. Unfortunately, as fuzzing and analyzing techniques advance, the number of vulnerabilities in XNU has increased rapidly in recent years. There are cases that the kernel vulnerabilities have been used to escalate the privilege of attackers and get full control of the system. For example, jailbreak the device. Accordingly, Apple have developed and deployed multi-security mechanism that can make the exploitation of the device harder. For instance, Apple deployed DEP, as known as Data Execution Prevention, and KASLR, as known as Kernel Address Space Layout Randomization, for iOS 6 and macOS 10.8. So what is DEP? It is a system-level memory protection feature which enables the system to mark relevant pages of memory as non-executable to prevent code injection attack. To break this protection, code reuse attacks were proposed. For example, ROP, return-oriented programming. Attackers could find gadgets in the memory and let the PC jump to them. To make these ROP addresses hard to predict, KASLR memory protection randomizes the location of virus memory segments, for example, code segment and date segment. To bypass KASLR, attackers usually need to leverage information linkage bugs or corrupt some kernel objects to obtain the addresses of gadgets in the memory. By using memory corruption bugs, it is possible to disclose the information of adjacent objects in the zone of in a same object size. In the previous version of XNU, the free list that contains all the freed kernel objects inside a zone uses the LIFO, last in, first out policy. Hence, the layout of kernel objects in the same size zone is predictable. To make the adjacent object hard to predict, Apple deployed mitigation called free list randomization in iOS 9.2 and macOS 10.11.2. When a kernel object is freed, the XNU will randomly choose the first or last position of the free list to store the freed element. In this case, it is hard for attackers to corrupt the kernel object in a zone in a predictable way. Unlike the free operations in user space, for example, the free function that only need one parameter, which is the address of the buffer to be freed. Freeing a buffer in kernel space requires an extra parameter, which is the size of the buffer. This is because the freed buffer needs to be returned to the zone once it was allocated. For example, in a keylog 256 zone, an attacker can use a buffer overflow vulnerability to change the size value of a VM map copy object to a wrong zone. For example, 512 zone. Then he can invoke a mark message to free this object. After that, the attacker can allocate a new kernel object through mark message with the changed size into the original zone. By using this wrong zone free attack, attackers can safely manipulate adjacent objects without triggering memory corruption bugs for multi-time. To mitigate this attack, Apple added a new zone metadata region structure for each zone in iOS 10 and macOS 10.11. This structure records allocation and free status for each object in a zone and gets panic when it detects the inconsistency between the actual size of an object and the size used in the free function. The main goal for the attackers is to obtain multi primitives to read, write kernel memory and execute arbitrary code, even in case that all mitigations are deployed in the system. But Apple deployed too many mitigations. But to corrupt the old kernel object is very hard. Therefore, attackers try to find a new kernel object which can be easily compromised. So this new target is the mark port. So what is mark port? A mark port in XNU is a kernel-controlled communication channel. It provides basic operations to pass messages between threads, and it can be used to represent resources, services, thus provide object-style access to these abstractions. In user space, mark ports are integer numbers like handlers for IPC port kernel objects. In the kernel, a mark port is represented by a pointer to an IPC port structure. There are 40 types of IPC port objects in XNU, and IO bytes field defines the type of it. IO references field counts the reference number of the object. Locking related data is stored in the IO log data field. Receiver field is a pointer that points to receiver's IPC space, for example, IPC space kernel. IP key object field points to a kernel data structure according to the kernel object type. As we mentioned before, the main goal for the attacker is to obtain multiple primitives to read, write kernel memory and try to execute kernel code, even in case that multiple mitigations are deployed in the system. So attackers leverage a special kernel object, which is IPC port, to obtain multiple primitives. By issuing system calls in user mode, Since the proposed method is mainly based on the IPC port kernel object, we call it mark port-oriented programming, as known as POP. Note that POP technique was not created by us. We saw it in many public exploits, and then summarize this code reuse a text for systematically study. Most of POP primitives are MIG messages. Luckily, XNU is open sourced, so we can download the source code and analyze the usage and behavior of each system call. To exploit the kernel through POP primitives, we need to figure out some addresses and offsets in the first place. So we can use ADA or JTool to analyze the kernel cache and help us to get the offsets. After analyzing the XNU source code and the kernel cache, we divided the POP primitives into 4 categories. The first category is general-purpose primitives. We know that mark subsystem in XNU kernel is a server that serves objects in various ports. This server receives incoming mark messages and processes them by performing the required operations to multiple resources, such as processors, tasks, and threads. Consequently, by using mark system calls, according to the designer's original intention, attackers can still achieve general and useful primitives without hijacking the control flow. Thus, we summarize this type of mark system call usage as general-purpose primitive. For example, mark represents the overall computer system as a host object. Through host-related system calls, a user space app can retrieve information or set primitives or set properties for a host. Moreover, with a send write to host privilege port and related system calls, for example, host process set privilege, an attacker can gain send writes to other powerful ports. For example, the process set port. These ports are very powerful that can be used to exploit and control the whole system. Besides, XNU provides a powerful set of routines, mark VM-related system calls, to user space app for manipulating task memory spaces. Giving appropriate privileges, one process can perform operations on another processor's memory space identically to its own. Note that mark VM-related system calls require the target process's task port as an argument. In general, a process only has the privilege to get its own task and memory space. However, with an information link vulnerability or an arbitrary kernel memory read primitive, the attacker could retrieve other task map pointers and craft fake tasks to manage other processors' memory space. Yes, especially for the kernel memory space. This is another type of primitive, querying primitives. It has a characteristic that the return value of the system call could be used to link kernel information. For example, speculating executed kernel paths. The code pattern of querying primitive model includes decision-making states and return value assignments. For example, mark port key object is a system call that retrieves the type of addresses of kernel object. It has some logic bugs to calculate some type of IPC port object, which help attackers to figure out the address of the objects in the kernel. For example, both Pangu and Taiji jailbreak used it to break KASLR in iOS 6 and 8 until Apple removed the address querying code in the release version. Some global kernel objects, for example, mark system clock, are initialized during the system booting and stored in a fixed place in kernel memory. In addition, clock sleep trap is a system call expecting its first argument to be assigned right to the global system clock, and it will return kernel success if the port name is correct. Therefore, if the attacker can manipulate an IPC kernel object and change its key object field, a side channel attack could be launched to break KASLR. Through memory interoperation primitives and type confuse attack, we can leverage some system calls to copy sensitive data between kernel space and user space. Especially some memory interoperation primitives are not used for the original intention of the design. For example, PID for task is such a system call which returns the PID number corresponding to a particular mark task. The function first calls the port name to task to get a mark task object, then invokes get BSD task info to get the BSD info of the mark task. After getting BSD info, the function calls proc PID to get PID number of the mark task and use copy out to transmit the PID number to user space. However, the function doesn't check the validate of the task and directly returns the value of task BSD info PID to the user space after calling the PID for task system call. Another example is limited kernel memory read and write. Just like dangling ports, just like dangling pointer, a port referring to a freed IPC port object is called a dangling port. System calls like mark, set, or get, mark port, guard, on guard. Some APIs, they can be used to read and write the member fields of the IPC port object. By default, IP contact field in the IPC port object is used to associate a user space pointer with a port. However, by using these APIs to a dangling port, the attacker can retrieve and set 64 bytes value in the kernel space. The last primitive is arbitrary code execution primitive. This type of primitive can be used to execute kernel code. For example, a rope chain or kernel function in arbitrary addresses. For example, clock get attributes is a system call to get attributes of target clock object. However, an attacker can change the global function pointers or just fake an object to hijack the control flow to achieve arbitrary code execution. This technique was used in the Pegasus APT attack in iOS 9.3.3. Besides, IOKit is an object-oriented device driver framework in XNU that uses a subset of C++ as its language. Therefore, its object contains a virtual table, as known as vtable structure. In user space, apps can communicate with IOKit user client, which are IPC port kernel objects with IOKit connection type. Consequently, if the attacker has the kernel write primitives, he can change the vtable entry of an IOKit user client to hijack the control flow to the address of a rope gadget to achieve an arbitrary kernel code execution primitive. Okay, let's take a look at a real POP exploit in the world. Yalu exploit. This exploit uses a heap buffer overflow to achieve a jailbreak in iOS 10. The vulnerable code exists in the mark voucher extract attribute recipe trap. This function first copies 4 bytes from the user space pointer, which is recipe size, to the SZ value. After that, it calls keylog SZ to allocate a heap buffer with SZ size. However, the function then calls copy in to copy recipe size the data from the user space to the kernel heap buffer. Note that recipe size is a user space pointer, which could be a very large number, but the buffer could be very small because it's only SZ size. Consequently, it will cause a buffer overflow. By using this vulnerability, it is easy for us to overflow pointers of IPC port object inside an OOL mark message. The exploit overflows those pointers and modify one IPC object pointer to point to a fake IPC object in user mode. The exploit creates a fake task in user mode for the fake port as well. After that, the exploit chain calls clock sleep trap system call to brute force the address of global system call and break the KASLR. In addition, the exploit sets IO bytes of the fake IPC object to IKOT task and craft a fake task for the fake port. By setting the value at the fake task plus BSD task offset, an attacker could read arbitrary 32 bytes kernel memory through PID for task without using any rope gadget. After disassembling the kernel cache, we can find that the function doesn't check the validity of the task and just returns the value on the specified offset to the user space. Finally, the attacker dumps the kernel IPC object and kernel task, and then he gets kernel task port through kernel get special port system call. After getting the kernel task port, the game is over because the attacker can use mark VM system calls to do arbitrary kernel memory read and write through the kernel task port. To prevent the attacker from abusing the kernel task, iOS 11 added a new mitigation that only the kernel can resolve the kernel's task port. So we cannot use the kernel task get special port trick on iOS 11. However, Ambeer proposed a mitigation bypass in a sync weak exploit that the attacker can copy reference pointer of kernel's VM to the fake task. Now the fake port has the same kernel address as the kernel task port. It's enough for the attacker to do arbitrary kernel read and write through mark VM related system calls. So note that most of exploit techniques we discussed in this presentation can still be used in the latest XNU. However, lots of companies, for example, our company Alibaba, offer MacBooks as work computers to their employees. There are some problems. Firstly, macOS is not forced to upgrade like iOS. Secondly, there are less hardware-based protections on MacBooks. Thirdly, macOS has less security sandbox rules than iOS. Consequently, it is hard for the work computers to defend against APT, and these computers need a more secure system. To mitigate the APT and POP attack, we propose a framework called XNU Kernel Object Protector, as known as XKOP. The basic idea is to load a kernel extension to the system. The kernel extension implements inline hooking for specific system calls and deploy integrity check for IPC port kernel objects. In addition, it could bring new mitigations to old macOS systems. The integrity check for the IPC port is implemented through the examiner functions. Therefore, our system needs to find reliable code points that the examiners could be executed. Chaos kernel subsystem exports a KPI that allows third-party developers to authorize actions within the kernel. However, the operation set is very limited. Mac functions is the operation set is very limited. We can't use it to do a lot of things. On the other hand, Mac framework is private and can only be used by Apple. In addition, the rules are hard-coded in the code of the XNU kernel. If we want to use Mac, we need to recompile the kernel. So finally, we choose inline hooking. Here is the architecture of inline hooking. Based on the examiners, XKOP replaces the original code entry of the target system call into a trampoline. The trampoline jumps to the examiner stored in the XKOP kernel extension. Thus, the examiner verifies the integrity of the target kernel object. There are 4 examiners are deployed in our framework. The first one is kernel object address checker. We know that IPC port object is a kernel object, which means it could not be in the user space address. So we check the address of the kernel object in some specific system calls. It's just like SMAP for old devices. The second checker is object type examiners. For example, in this case, in the getBSD task info function, the A1 should be a real BSD task info structure with a valid PID number. If the examiner finds the PID is invalid, it will cause a warning or panic according to the user's configuration. The clock sleep trap is a system call that can be used to guess the address of global clock object through brute force attack. But when the attacker to do the brute force attack, he needs to get a lot of error returns in order to guess the address of the clock object. Therefore, we implement querying examiners, which count the error returns in a window time, and then warning the user or panic the system according to the configuration. The last examiners is kernel task port examiner. Kernel task examiner. It first brings the task conversion evil mitigation to old macOS systems that only the kernel can resolve the kernel's task port. After that, it will check the task's VM object. If the caller process does not belong to the kernel and the target's IPC port object has the same map structure with the kernel, which means it has the same space memory with the kernel, the examiner will trigger an error return or panic because only the kernel can modify its kernel space. The user space applications should not have any permission to do that. For evaluation, we selected 4 kernel vulnerabilities and available exploits to evaluate the effectiveness of our system. We first ensure that exploits work on the corresponding systems, and then we deploy the XKOP framework and run the exploits again to check whether our system detects and blocks the attack. As we mentioned, as we showed in the pictures, the experiment result shows that XKOP provides deterministic protection for every vulnerability and block each attempt to exploit the system. For example, the YALU exploit, it uses PID for task to do the kernel memory, arbitrary kernel memory read. First, it uses port name to task to get a fake task, but our examiners find this task is not in the kernel space. It was created in the user space, so it will show a warning to the user. But after that, it uses PID for task to get an address in an arbitrary kernel address. But the PID is invalid. It's a very big number, but the actual PID will not as big as this number. So our examiners will check the valid PID number and warning the user that the examiners find a real POP attack. Unfortunately, our framework cannot mitigate all kinds of POP primitives. Firstly, for the querying primitive, which uses error return values to gain an extra source of information, which is very similar to the side channel attack. For the side channel attack, it is an attack based on information gained from the implementation of a computer system, rather than the weakness in the implemented algorithm itself. So it's very hard to protect such attack. Secondly, we didn't implement any protections for arbitrary code execution. The reason is without hardware support, software-based CFI implementation can be very expensive. In addition, modern kernel could be patched by pure data, which means kernel memory read and write primitives are enough for the attackers to accomplish the aim. Last but not least, we may miss some potential vulnerabilities that can bypass XKOP protection. As an imperfect solution, our system supports extensible examiners to prevent new threats in the first place. So here is a conclusion of my talk. Firstly, we discuss the mitigation techniques in the XNU kernel, which is the kernel of iOS and macOS, and how these mitigations make the traditional exploit techniques ineffective. Then we summarize a new kind of attack called POP that leverage multiple IPC port kernel objects to bypass these mitigations. Besides, in this talk, we not only discuss the attack techniques, also we propose a defense mechanism called XQP to protect the integrity of the kernel object in XNU. So if you have last but not least, if you have any questions, you can follow me on Weibo and Twitter and ask me questions. So here is some materials for this talk. It's very useful. And that's all for my talk. Thank you for your listening. Is there any questions?
So have you played about with Fuse, file system in user space?
What?
And implementing, similar sort of system under Fuse, because I can see that there's similarities here, and I can see where they would be exploited similarly.
Similarly,
Yeah.
do
you know Fuse?
Fuse?
Yeah.
You mean memory fuse or
File system in user space?
a file system in
Yeah, it's basically an implementation of the the system call interface, if you like, but it gives,
yes, but our system only protect the port-related objects, kernel objects.
But you can still do copy in and copy out via Fuse.
You can. I'm not sure about that. You can talk with me later after this.
Okay. Yeah.
Okay. Thank you.